Jæja. All right. So you know the word jæja? You non-Icelandic speakers, you know the word jæja? No? Okay. It's basically whatever, well, let's go, or really? So depending on the way you do it. So you can get by with jæja on lots and lots of occasions, right? Yeah. Okay. Yeah. So just the way you say it, basically, you get by. So yeah, this is a very serious one. Let's talk about transactions, and let's talk about recovery. So just to refresh, let's talk about issues that arise with buffer management. So first, what's stealing a page? Yeah. So it's basically you are a transaction, you need some space, somebody else has updated page, and you steal the slot, you steal the memory space. So that page goes to disk, right? So this is stealing a page. And so the effect is that you have data on disk that is uncommitted, right? Which is a problem. So what did we do to get around this problem? We log, and what do we log for this particular problem? The old value, exactly, so that we can undo. All right, good. 2 people know this stuff, for sure. Maybe even 10. Okay, what's forcing a page? Or what does that mean, to force a page in this context of buffer management? Yeah, you're forcing page to be written on disk, and on what particular occasion are we basically referring to? So this is basically the commit. Forcing a page means that when we do a commit, we actually take all the updated pages and we write them to disk. We like the steal, right? Well, we kind of have to have the steal, because otherwise the buffers may fill up and we may just abort transactions because we don't have space, right? Do we like the force? Not really. One of the reasons is that it can take a long time to write everything to disk, so it may take a long time to commit. We can't really do it autonomically because there are many, many IOs. And if you have, let's say, a counter here that is continually being updated, then you will have an IO for every instance of the update rather than just a few. And so to get around the problem of having data, basically the result is we may have data in memory that's committed, but not on disk, right? So how do we fix this? With the log. And what do we write in the log for this particular problem? The new value. All right. Anyway, are you clear on this? That's really the fundamental thing of this, knowing what happens with the buffer management and what do we log. Now, we had the rules about the log. Remember those? There were 2 rules. One for the steal, one for the no force. Do you remember them? Together we called them WAL, WAL, meaning right ahead logging, exactly. So the L is the logging, but the other one is the right ahead. And basically what it means is that you write the log ahead of the actions you do. So before you write something to disk, you write the log. Before you commit, you write the log. That's the write ahead. And so, do you remember the rules? Let's say for the commit, before you commit, what do you ensure with write ahead logging? Before you commit transaction T, let's say. Anybody? Until log records, yes. Okay, so basically for transaction T, you need to make sure that all the log entries for T are on disk before you can commit. That means that if you need, for some reason, to redo it, you can do it. Okay, so that was one of the parts of write-ahead logging. For the steal, when we're writing a page that shouldn't be there, what do we need to enforce with write-ahead logging? We need to flush everything up until the log record for this particular write. So the last log record that wrote this page, we need to flush that. And that's again the write-ahead logging. We write the log before so that we can undo. And so this is really the logging part. It's really this, that we need to make sure that the log goes to disk before the actions that it's yeah. Is there any reason why you wouldn't want to flush everything since you're doing the I/O anyway? No, there's no reason, and you do. So basically, for example, for the write-ahead logging rule, technically, let's say that you're writing, this is transaction T. Actually, it should be on this slide. This is transaction T, and you need to flush everything. Technically, you only need to flush this. What happens is that you flush the whole thing. And remember, we talked about that it's okay to be ahead in the log. It's perfectly okay if there are things in the log for transactions that haven't been committed. They will be aborted anyway, it doesn't matter. So you will typically have the log being written kind of continuously to use the bandwidth of the disk so that you never have to wait for it longer than necessary. So this is a very good question. No, there's no reason. In fact, you would do this. So, all right, thank you. So that was the steal no force thing. We support steal no force, and this is why we need the old value and the new value. All right. So we talked about the algorithm that we do this, and this is basically it. We need to analyze the log to figure out which transactions were alive. We need to analyze the log to figure out which IOs may not be on disk. And then remember, we redo everything, absolutely everything, and then we undo the transactions that should be undone. So this is the overview of the algorithm. And then what did we have? We have the data structures. So we talked about the log records. We have transaction ID, page ID, and also actually the, remember this one, the log sequence number. So log sequence number, transaction ID, page ID, which page was written. And then remember these guys. We had offset. So within a page, we basically have offset and length, which indicate how many bytes were written and where in the page. And then we have the old data and the new data. And what else is important? Okay. So the other thing that happened basically when we are undoing. You remember what we did? When we wrote, we have a record like this. We keep track of the page ID, the offset and length, and old value and new value. Do you remember what we did when we were undoing things? So there are two things you need to do, right? The first, you need to modify the page. That's one thing you need to do because you are undoing. So you take the old value and you put it into the page. What's the other thing that we do when we are undoing? We write a log record. Do you remember what this was called? So CLR, that's the abbreviation. Let's see if this brings. So L would stand for log, R for record. And since we are compensating for the action, what is the C standing for? Compensating. That's a strong hint. So it's a compensating log record. So it's basically when we do the undo, we sort of compensate for the first write by putting in the value, and then we make a log record of this. And it's basically the same. It's like an undo, except we had this one pointer, remember, that was pointing to the next thing to undo, the undo next LSN. And that's it. That's the only difference really between these two. And the point is that in the redo, we redo this, we redo the CLR also. Okay. So you roughly have, roughly remember this. Then we talked about what's happening in normal processing, which is basically when you are making the update, you create a log record, you store the LSN in the page, and you unlatch it. And then you're done. So you take a little lock, like a semaphore, on the page. You can update the page, you can create a log record, you can store the LSN into the page, and then you free it. And that's it. So there's no I/O. When you're updating a page, there's absolutely no I/O involved. When do the I/Os arise? Who decides to do an I/O? The buffer manager. Yes. So when you're doing the transaction processing, no I/Os happen because of you. It's all in the buffer manager. So that one is deciding, if you do need page, it's indirectly because of you, but not directly. So, a very common mistake on an exam is to assume that everything gets written on commit. So things do not get written on commit. All right? And after saying this 3 times, some people will think that things get written on commit. So, but that's not you. Those are the ones that are not listening to this. Anyway, we're not forcing exactly. And so it's really important to remember when you commit, something goes to disk, yes, but it's a log, and that's it. When you commit, you release your logs, yes. 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 So basically, right. So does it have to be written before you read it? So yeah, you can read the data from memory. That's fine. But what you need to make sure is that you first write the log, and then you release the logs to commit. So you have to make sure that the log goes to disk before you release the logs. No, then it's basically just waiting until you release the lock. If you have a read request from somebody else, they have to wait until you release the lock. And at that time, the log record is on disk. And so you have committed, and they are reading a value that is safe. But they're reading it from memory. Because, again, remember, you don't force anything. You don't, you basically, what happens is that you had a page in memory, and that one got modified somehow. And then, you have the log, and that one goes to disk, but this one here stays in memory. And so with the change. Now, the reason why somebody couldn't read your value was basically because of locking. And once you release the lock, it's available for everybody else to access. So again, we have the assumption, well, what we're talking about now, we have the assumption that there is locking. So remember, we have this discussion about the multi-version concurrency control, and that's a little bit different. But in that case, it's the multi-version that is keeping people from reading your stuff. But in any case, things stay in memory, and that's the important thing. What gets flushed to disk is the log. And if you follow the right-hand logging, then you're safe. So it's a little abstract, it's a little tricky, but turns out it's the way things happen. Okay, so the undo, we write the compensating log record, and then we undo the changes. When we commit, remember we force write the log entry, and that's about it. We remove things from the transaction table. And then we talked a little bit about the checkpoints. And so remember, there are kind of 2 checkpoints. One is a hard one, where you write everything to disk, which is expensive. And then we have on the other side, we have the fuzzy, where you write the transaction table to disk, and you write the state of the dirty pages table to disk. and that's it. You don't write any IOs to disk other than that. Probably in most cases, the systems might do something that is in between. They might do some flushing, but then save some state. Depends on your system. And then we talked about what's in this. Okay, so this is the overview of the data structures, and now we're going to go into the algorithm. And let's talk about analysis, redo phase, undo phase, and what happens in repeated crashes. So overview is basically we find the last checkpoint, and remember that one has the state of the transaction table and the dirty pages table. Then we go through here and we update these two tables to know which transactions were were alive at the crash, because we need to undo them, and we figure out which pages are possibly dirty. So it's not entirely clear that they're dirty, but they're possibly dirty. Then we do redo, where we basically go through from the oldest log sequence number in the dirty pages table, and we just redo everything. Repeat all the changes. And then we find all the transactions that were alive or loser transactions, and we undo them. And when we're undoing, we're adding the compensating log records to the log, so the log gets a little bit longer. So this is the overview. So I'm gonna basically have a running example. So I'm gonna give you the right one. 1, 2. And if you're listening to this at home, it should be it's probably on the next slide, and print it out and work with it. Oh, and so this has basically this log sequence, and so we're gonna work with this. So the first thing that I want you to do is to remember in these log records, we have something called the previous LSN. It's a linked list showing what's the last thing that this transaction did. And I want you to basically draw with arrows the linking of the prev LSN in this particular case. And the assumption there is that we have a transaction table which has a transaction something like T2 pointing here, and then we can trace our steps using this prev LSN until the end of the transaction. And you can raise your hands if you're done. If you need a hint, I'll draw one. Basically saying the previous log sequence number 260 was 20, because that's the same transaction, but it's the last thing this transaction did. So the TT, DBT, this is the transaction table and the dirty pages table. This is just indicating that in this record they are empty, because it's a checkpoint at the start of the log. So you done? Done? All right. How many arrows do you have? 4? 1, 2, 3. That's pretty convincing, actually. All right. So we have this arrow that I drew. What's the previous LSN of 20? It's a null or something, right? So it's often drawn like this, the ground symbol from electric diagrams. It's a null. Okay. Or yeah. So it's not. I probably would fail my electricity courses. All right. The previous LSN of 50. What's this? It's a null. Yeah. The previous LSN of 45. 40. Previous LSN of 40. 30. Previous LSN of 30. 10. And then this is null, right? You had something like this? Maybe better drawn. So it's basically just linking, and the point is that each transaction is linked separately. That's really the point. And if you have a pointer to the transactions, then you can trace all the actions of this. Why do you need this list? It's for the undo, so that you can find everything in the transaction and undo it. For the redo, we don't really need this list because we can just go here and just go through everything. All right. Now, I want you to, so the next thing, so we get this drawing, which is, slightly better drawn than I did. What we do in the beginning, we go find the begin checkpoint, we scan until we find the end checkpoint, and then we read in the transaction table and the dirty pages table. These happen to be empty. So we get this state. Now I want you to go through these steps, and I would like you to update the transaction table and the dirty pages table according to the algorithm that we had. And do you remember this one? When you see a new transaction, you put it in the transaction table. If you see a new record of the transaction, you update the last LSN of the transaction table. When you see a new page, you put it into the dirty page table. But when you see another update to the same page, what do you do? No. 50-50 chance. No, you actually do nothing, because if, for example, with page 5, if you overwrote it with 60, then you would lose the fact that you did an IO at 10. So remember, transaction table, you overwrite, dirty page table, you don't. It's okay. You will do this correctly in an exam, I know. It's a good time to fail. Nei, það er bara þetta og þetta. Já. So the transaction table only has the transaction ID and the last LSN. So you don't have to worry about the date, about the page names there. And then the dirty page table only has the page IDs and we call it the rec LSN. If they had called it the first LSN, you would have been better off. So we have the transaction ID and the last LSN, and then we have the page ID, and we call this the rec LSN. We're tracing Aries. So maybe to get you started, if you are struggling a little bit, let's do the first one. When we go to record 10, we basically see both a new transaction and a new page. So first you put it into the transaction table, the transaction ID, and I'm kind of ignoring this. Let's not worry about this. Transaction ID and the last LSN. And then into the dirty pages table, I put the page ID and I put the rec LSN. So then at this point, we have one entry in each. And if you, it's a good thing now to then think about what happens with the next log record. New transaction, new page. Who's done? You're done. You think? You do. Who else? Yeah. You're done. No? You can do it. Who's done? Yes? Good. Yeah, exactly. I like this. So the important and they count as actions of the transaction, so they do change the last LSN, but of course they do nothing to pages or anything. Yeah. And again, this because we were drawing the prev LSN, it basically indicates what you need to do. So next thing, 20, what happens? It's basically the same, right? You need to put a new transaction into a transaction table, and you need to put a new page into the dirty pages table. Then transaction 1 abort. What you do? Just modify what? The transaction table. Yes, okay. Then you get the CLR. Which page is being written with the CLR? It actually doesn't say in this log trace, but which page is being written? P5, exactly. Okay, so when we do this, what do we do? What do we do to the transaction table? So we don't take T1 out of the transaction, we do that at end. So next turn, we do this. Yeah, we update the value of last LSN, so to 40. What do we do to the page, dirty pages table? Because we're writing the page. Nothing. That's the tricky part. Resist the urge to change the rec LSN. Because if you do change it, you lose the first IO. You cannot keep track of it. This is important. Why do we need this compensating log record? Here, it's basically okay. Yes. So what we do later on, so the question, why do we need this rec LSN? What we will do later on is we will find the mean of this and we'll start redoing from that. So this is exactly your point. We need to keep track of this to know where to start to redo. Yeah, very good. So again, we update the last LSN with 40, but we don't update the dirty pages table. 50, that's the end. What do we do there? Oh, sorry, 45. Now you can answer what you said before. Now we remove it. And so this is the trick now. Now it's ended. We know the abort has completed. We've undone everything. It goes. If we had a commit, then we would basically have an end also, and then we'd make it disappear. 50, T3 writes P1. What do we do? Yeah, put it into the transaction table and also into the dirty page table, right? Because this is the first time we see P1. And then 60, what do we do there? Yeah. So we just see a new action for transaction which is already in the transaction table, and so we just update the last LSN. But again, we don't change the rec LSN in the dirty page table. Very important. Very common mistake. Okay. That's a complete. So if you think about when do we remove things from the dirty pages table? So just in normal processing, when would we remove things from the dirty pages table? When we write to disk. So when the buffer manager decides to write something to disk and remove it from memory, then we remove it here. No, you wouldn't change the LSN. So yeah, you only remove, and so when you write it again, it comes in with a new LSN. Yeah. So, for example, if you imagine this case where there actually was no crash, so you're just processing, and at this point, the buffer manager decides to write P5. What would be the rec LSN of P5 in the dirty pages table in this case? It would be 60, because when you wrote it, the entry disappeared. And then when you have T2 writing P5, you bring it back into the dirty pages table and with a rec LSN of 60. Very good. So this is basically the way to update the rec LSN is the buffer manager writes something, it disappears, and then because there's another write, other update, then it comes back in. You're not really changing the entry. No, exactly. You're not really changing the entry. It's just, there's a delete and then an insert with a new value. Yeah, precisely. But so now, what if the buffer manager wrote P5 here, and then you have a crash? Yeah, sorry about the font. So I'll redo this. Right, P5. And so there's nothing in the log. It's just we know that the buffer manager wrote P5 there. And then we do the analysis. So it crashes, we come back up, we read the log. How is the dirty pages table different? I mean, we know that we kind of, if we did this, it would be correct, right? The redo would work correctly. Can we do that? Can we change this? What do you think? Yeah. So the crash is still here after 60. And we didn't do another checkpoint or anything. It's just, it crashed. It's tricky, right? I mean, there's nothing in the log that indicates that the write happened. So how could we know? We don't. That's the answer. We can't. Even if the write actually happened, we would get exactly the same dirty pages table. And so remember I said this is basically the table of pages that are possibly not written to disk. And so this is a case where the page was written to disk and it's not here. And even what might have happened is that, even more interestingly, you might have the write here. So just before the crash. So all the changes to P5 are on disk, but we don't know. So we get to, I mean, there are ways to know. So remember, there's something called page LSN on the page. And so basically, if this happened, we would see on the disk that in P5, the page LSN would be 60. So this is the way we can know. But we have to actually bring the page in from disk to know this. But if we find this out, then we can avoid writing it. We can avoid updating. So anyway, so you're clear on the analysis? Could the same thing apply to transaction table? Could there be a transaction that ended and was not in the transaction table in regular operation, but it is in the transaction table here? No, because we do the end record, and that's when you remove. So transaction table will be the same. Dirty pages table, there might be IOs represented here that actually went to disk. And we need to worry a little bit about this. So that's the analysis. Let's take a 5-minute break now, then come back and talk about how do we then redo, decide what to redo and what to undo. Okay, so we did the analysis. And so the next phase is the redo phase. Right, this is a slide with the running example. So the questions think about this, where does the redo start? And we actually had the question to this. We go through the recolescence in the 30 pages table and we just find the smallest one. That's where we start. And then, again, a little bit surprisingly perhaps, we just repeat everything. Even the things that we know that we're about to undo, we still repeat them. And remember why we do this? It's easier. So in terms of effort, maybe not, but in terms of the logic of it and understanding, it's actually easier. And then, so we basically recreate the database state at crash. Now, it doesn't mean that we write this to disk. It gets updated in the buffer manager, and then the buffer manager decides what goes to disk. Now, if we happen to crash during the redo, well, maybe some IOs went to disk. We don't know. It's a choice of the buffer manager, but typically you would see no effect. Things are updated in memory, and then, it crashes, and so you lose those updates. So that's typically no effect. Now, but there are ways that we might skip on updates. And we talked about one of them before, when we actually find that a page, we are looking at a particular log entry, and we find that the page LSN is that log entry or something bigger. So we are looking at the log here, we're looking at entry 20, and we go and we look at the page, and we find that it's indeed 30. What does that mean? The page got written after this. So we don't have to redo this. You follow? So the page LSN refers to the last update that actually went to the disk. And so at some point, so 20 refers to page 1, 30 refers to page 1. And what happened, and then maybe we have a 40 that's referring to page 1 as well. And so what happened when we were operating is that between 30 and 40, the buffer manager decided to write P1. And when it wrote P1, it wrote all the changes up until 30 and made a note that this is indeed IO30 that's represented here. And so this is one case. So we still have to read the page to check, but if we find it, we can avoid it. Now, there are other cases. For example, if we are looking at an update for page 1, let's say, so just to keep with this example. And in the 30 pages table, we actually don't have a page 1. We have page 2 and page 3, but we don't have page 1. So, and this could happen. We'll look at when, but basically, this means that at some point, there was a redo, there was an update to page 1, and then it got written to disk. And we know of this. And the trick is, essentially, let's say here, there's a checkpoint. So we write P2 here, or P1, sorry. And then we do a checkpoint. So here we have 30-page table. It has P1, it has P1, it has P1. We write it, P1 disappears, right? It's not in the table. We make the checkpoint, and P1 is not in the table. But then we had an update to P2 here, sorry, at time 10. So P2 and 10 are in the 30-page table. And this means, remember, we start the redo phase from 10. And then we hit 20, and we check, is P1 in the dirty page table? No, it's not. So that means the update is on disk, right? Is this clear? And so the other thing that could happen is that the page is actually in the dirty pages table, but with a larger recollection. How could this happen? So we're looking at, let's say, 20. We're looking at page 1 being written, but we have page 1 in the dirty page table, but with 40. Yeah. So yeah, it was written on disk, and basically it was written at, sorry, this time. So, and then there's a checkpoint here. So page 1 is now in the dirty pages table, but with 40. When we wrote it, it disappeared. Then to disk, then we update the page again. It comes into the dirty page table with the recollection of 40. We do a checkpoint, and so it's in the dirty page table with the recollection of 40. And then we do the redo phase from all the way from here, and we see 20. Well, 20 must have made it to disk. We see 30. 30 must have made it to disk. We see 40. All right, we got to redo this. Clear? A little tricky. Now, you could basically redo everything, and you would be fine. Basically, you just write all the pages. This is simply to save work. So the first two, how many IOs will you save because of the first two rules? You will save one to read the page and then one to write, possibly. Not necessarily, but possibly. This one, the third rule, you have to read, but you don't have to actually do the update. So that's it. And you don't change the log at all. You just make the updates in memory. Maybe the buffer manager decides to flush to disk, but this is not your concern. So in the case that you have, where the recollections are 10, 20, and 50, we basically go to here and do all the updates. And remember, we redo the updates and we redo the compensating log records because they are actually updates as well. So a typical exam question it would be which log record numbers are redone, and just remember the compensating log record numbers. Those are typically forgotten. So I actually put a slide about this. When do these cases arise? And for example, for the first case, make try to think of a log patch where you would find this case. The page is not in the dirty pages table when you try to redo it. We kind of gave you the answer already, so you have to come up with a sequence that allows you to do this. Think about what it would look like. You are redoing, sorry, and you find a page that's not in the dirty pages table. Can you describe how you do this? What do you need? You need a checkpoint, right? You need an update. You need the buffer manager to write, and then you need to register this write by making a checkpoint. When the checkpoint doesn't have the entry, and then later on you rewrite it again. Or actually, in the first case, you don't. So, excuse me. What triggers the checkpoints? So checkpoints are typically done regularly, just on a time-based basis. So every 60 seconds or something, depending on your activity. So it's an automatic thing that happens with the system. So if we look at the first case, can we draw something like this? We have, let's say, transaction 1 updating page 1. We have transaction 2 updating page 2. Okay? And then we can sort of indicate, all right, so we have a write of page 2. Sorry, that was not 2. So now we do a begin checkpoint and we do an end checkpoint. What's in the end checkpoint tables? Transaction table has what? T1 with 1, 2, sorry, 3, 4. T1 with 1, right? And T2 with 2. Dirty pages table has P1 with 1. Okay. All right. Do we need anything else? We get a crash. Should we have T2? Yeah, it's in the transaction table. Yes, yes, important. But P2, no, because we wrote it, it disappeared from the transaction table. So that's the trick, really. So in the log we don't know this here, but we're just basically simulating this. And so when we did the write of P2, it disappeared from the transaction table. Then we do a checkpoint, and then it's not there. So what happens now in redo? Which actions get redone? The first one gets redone because 1 is the smallest record send in the transaction in the dirty pages table. So we need to redo this one. The second one, well, we basically won't find it in the transaction table, right? In the dirty pages table, sorry. Because when we do the analysis, we go to the last checkpoint, we read it. There we get the first instance of the transaction table and dirty page table, and then we scan to the end of the log. But there's no more log, so we don't change them. So this is, yeah. Can there be something between begin checkpoint and end checkpoint? Yes. So basically, the tables in the end checkpoint represent the state at the begin checkpoint. And the reason to do this is that you make a memory copy at the begin checkpoint, and then you allow transactions to proceed. And then you write the log record at the end checkpoint. And so it's a little complication, but basically that's it. So there could be any number of log records between. No, actually what you do, so the question is, wouldn't they be lost? What you do basically when you're analyzing is you start from the begin checkpoint. You find the end checkpoint record, read it, and then you start from the begin checkpoint. And that's the trick. So it turns out they wouldn't get lost. But a very good question, indeed. Okay. If there was no checkpoint in the log before the crash, so if the crash is here, for example, what would be the dirty pages table in this case at the end of the analysis? Well, basically, okay, yeah. So what the system always does in the beginning is to do an end checkpoint, or begin checkpoint, end checkpoint. So you always have something to start with. So the dirty pages table in this case would contain P1, 1, right? And then P2, 1, 2. Agreed? Okay, so all right, so I see what you mean. Well, let's assume that this was the beginning of the state. So you have transaction table is empty, you have dirty pages table is empty, and do it correctly. This is number 1, 2, this is number 3, this is number 4, this is number 5, and this is number 6. So just to be clear. So basically these tables are empty, and so that's all the things that happen. You had 2 IOs. So in this case, the dirty page table would contain these 2 pages. And this particular rule wouldn't apply, right? You would just miss the fact that you wrote it. Which rule would apply? Assuming you wrote P2 after, just before the crash. What's the situation then? Yeah, the last one. When you did that, you wrote the page LSN, which is now 4, to the page. And so when you read again, you discover that you actually did the write. So if you do happen to make the write, you can discover with the third rule, which means you don't have to do the update. But if you have writes before the last checkpoint, then either of the first 2 rules applies. If you have the write after the last checkpoint, then the third rule applies. And this is indeed the assignment number 6 to learn this. First one is to trace the operation, and then second one is to figure out instances where these rules apply. So anyway, yes. The LSNs, they are endlessly growing numbers, yes. Now you can, when you're truncating, you can sort of rotate them, and so you don't need, don't get into the Google counter problem where you just overflow, right? Yeah. So remember, when we do a backup, we can truncate the log, and so basically at some point you can recycle and go back to 0, and you just need to be aware that you did this. Or alternatively, when you do the backup, you could start again. Just start with 0 or something like this. So it has to do with backups, that you can truncate the log and you can do this recycling. And after that, it's just a matter of how you implement it. So we have these rules. Can you think of a log where this particular rule applies? So you've done the analysis, you have a record, an entry for the page in your dirty pages table, but it's an IO after the one that you're looking at. How could this happen? Try to see if you can come up with. And basically you need the checkpoint. It didn't flush the logs. Well, you have to make sure, assume the logs get flushed. Update, write, checkpoint, update. Exactly. This is what you need. So you had an update, it got written, so it disappeared from the dirty pages table. You make a checkpoint with that dirty pages table, and then you write it again. Now there's one more trick to this, which is, let's look at another case. So we start with begin checkpoint, and then checkpoint with the the empty tables, and then we do transaction 1 updates page 1, transaction 2 updates page 2, and now we write page 1. Okay, and then we do the begin checkpoint and we do the end checkpoint, and The dirty page table here would contain what? P2. 2, like this. Fair enough. Now, do the redo phase. Which updates are tried or are considered and which updates are redone? And do these rules apply? Think about this. What does the redo phase look like? Yeah. And actually, sorry, I messed up. So this should be 1, 2, 3, 4, 5, 6, which means that this should be 4. Yeah. So we start where? We start at 4, right? The smallest rec LSN. And we would redo this. Agreed? Because we wrote page 1, but we didn't write page 2. So did we use this rule? Did we use it? Did we? We actually didn't, because we didn't look at this particular log record. So we need this one more condition for these rules to apply. They actually have to be considered. And for that, you need a previous IO. Before, remember, we wrote actually P2 here. And in that case, we started here. And so we did consider both. So that's the interplay of this. We start processing with the first IO that was possibly not done. And then we look at them all. And sometimes we find things that were written in the checkpoint, that was recorded that they had been written by not, basically the checkpoint didn't contain them. And then sometimes we find that we cannot look at the dirty pages table and figure out, but we can actually read the page on disk and we can figure out that it's been written. So these are the ways to save IOs, and they have to do with the checkpoints. Clear enough? So tomorrow you have the assignment to write this up yourself, make some examples, and so you should basically start. Don't go back to the lecture and just copy. Do it yourself, and then retrace the whole algorithm to make sure that it's correct. If you can do that, you're starting to have a fairly good understanding of this. So that was the redo, and then the final phase is the undo, and that basically we need to undo all the transactions that were active. And the way to do this is, we could basically take one of them and undo that. But it's slightly more efficient to undo them in order somehow. And so we keep a track of the next thing to undo, which is typically the last thing that each transaction did, and then we just go back in the previous LSN. And then we pick the largest LSN. If it's a compensating log record and we are at the end of the transaction, we're done. If it's a compensating log record and it's not, then we just update the set. And if it's an update, then we do the undo, we write the compensating log record, and then we add the previous LSN to the undo. So I'm going to go through this. So this is probably the most tricky phase. So if you look at this, the live transactions were actually T2 and T3, right? And so we need to undo all the operations of T2 and T3. Okay. With me on this? And what we're going to do is basically undo them in this order. So we're going to go backwards in the log and undo them. And to do this, we look at this here and say, the things that I want to, the first thing I want to undo is one of these, because those will be the last things in the log. So I'll put them into the undo set, which now has 50 and 60. Then the first thing to do is to say, I'm going to undo this. So how do I undo? I write a compensating log record, and I actually do the undo. So we get this, right? We get a new compensating log record that is saying T2 is now undoing 60. And because we want to keep track of where next, then it's going to say the undo next LSN is 20. So this is actually the tricky part of this. Do you remember why we did this undo next LSN? It's just to skip past all the previous sense. Points directly to the next thing to undo after this one. If we now wrote this to disk and we crashed, we would redo, we would find actually that 60, sorry, this would be 70 or something. We would actually find 70 in the transaction table if we crashed again. And so what we do is to find that, and we say, okay, that's a compensating log record. We'll traverse the undo next LSN directly to 20. So we don't have to go through all the prerequisites. Now, if we have a long transaction that starts to make sense, we can just jump right back. So we insert the 20 to undo. So now the to undo is 20 and 50. And you can see we undid 60, and so we have these two remaining. Fair enough? So we undo 50. How do we do this? We write the CLR, and then we do the undo. And what's the CLR going to look like? It's basically transaction 3 undoing LSN 50. What's the undo next LSN for T3? It's null, because that was the first action of T3, and so the prev LSN of 50 is actually null. And now we found that this was the end, so we write an end record for T3. Now if we crashed and we restart it, we would actually find that T3 basically wasn't there at the end of the analysis phase, which is correct, right? Because we have already undone, we redid the update here, we redid the undo here, we did the end, it's done. Okay, so this would be then in this notation 80 and maybe 90. So what goes into the to undo set for this? Trick question. Nothing, because we just removed the transaction. So the size of the to undo set is always the number of transactions that we have still to consider. So when we found the end of one of them, it shrinks, and then eventually it's empty. So now we remove this from the transaction table, and now the to undo set is smaller. Next thing to undo, the smallest thing in the to undo set, which is 20. How do we do this? New CLR, undo of transaction 2 for LSN 20, and the undo next LSN is null. T2 ends, and so we can remove T2 from the transaction table, and we put nothing into the to undo set, and then it's empty, so we're done. And so one by one we go back into in time in the log, and we undo the actions, and you can see that the CLRs are in reverse order of the updates, and these undo next LSNs, they point past all the updates you did, all the undos you already did. And so if you crash again, then you will repeat this, but you have nothing more to do. So you will again repeat your history. It's a little bit unlike the redo. Remember, if you crash in the redo phase, you just lose your work. Here you actually make more work. If it gets written to disk, then you're redoing it rather than undoing it. So in repeated crashes, the redo phase gets longer. the undo phase gets shorter until you're done. So that was actually this. All right. So this is an example of repeated crashes, and you can see basically the log will look exactly the same with repeated crashes as it would with a single crash. And if you had abort records, you would basically have the same compensating log records and the same end records. So if you actually decided to abort your transactions, the log would look almost the same as well. You would just have the abort records. So this is the algorithm. Now, the assignment tomorrow is again to trace one operation and then to, make examples of where you can apply these rules that we were talking about in detail. But I would recommend to maybe run some more, trace the algorithms a few times, because if it's the opportunity tomorrow to do this, otherwise you will forget. It's tricky, right? And it's I know this by heart by now, but I remember the time when this was very hard and a little bit painful. But the thing is that it's once you understand the buffer management issues, once you understand, basically once you figure out that the buffer manager is doing the writing to disk, whereas you are doing the updates to the log, then some of these things make more sense. Any questions at this point? Yes? Mm-hmm. Yeah. So the question is with transaction table and dirty pages table, what is the last state we have when we have a crash? And this is exactly, you have the last state of the last checkpoint. And so if you haven't made a checkpoint since the beginning, then they will be empty in the beginning. If you have a checkpoint somewhere, then you will start with these, and then in the analysis phase you will update them. Yeah. So it's exactly that. And yeah. And so the point of the analysis is actually to rebuild these tables. That's the whole point of the analysis. And then the redo phase, it's using the dirty pages table. The undo phase is using the transaction table. And if you go through this, you'll find that the redo phase doesn't look at the transaction table at all, and the undo phase doesn't look at the dirty pages table at all. They're really working on different tables. More questions? All right. So how's the project going? So I gave you an extension, right? It sounded like you were a little bit crammed with deadlines. Was this correct? Yeah. Okay. So hopefully it helped a little bit. This means you have an opportunity to ask me questions in a moment. Well, we can just turn this off and then you can ask me questions. And then there's the midterm, which will be held next Tuesday in this class at 12:20, from 12:20 to 2 or whatever, 13:55 or something like this. So I will be away. Grímur, who's going to take over as teacher, will be here looking after this. And it's basically, you will see some old midterms. It's something similar. 5 questions, 20% each. Remember, the midterm is either 0 or 20%, depending on how well you're doing it. And it's basically 20% of the sort of basics versus simple query processing, 20% of the joins and all this stuff, 20% of query optimization, 20% of current condition control, and 20% of recovery. Very simple. And it should be doable if you're well prepared, in an hour and a half. So, any questions about this? it's closed book. You will get a formula sheet, which is already on my school. So you can look at this. You will get this with the exam. You should not have to use the formula sheet. The examples are simple enough that you can think your way through them. But the formula sheet will be there if you need it. Is there a need for a calculator? Well, if you go with the formulas on formula sheet, you good, but you can basically do the whole thing, trace the algorithm on page. So I would say, if you how to say, if you need to use the calculator, you're doing things too complex. It's allowed. Simple calculator, non-programmable. See, your laptop is a calculator, right? Yeah. All right. Any questions about this? All right. So one thing I want to mention, I sometimes get the feeling that when people are preparing for exams, they look at the exams and they learn the things that are in the exams. But of course, exam is a random sampling, and it's not so very likely that you will get exactly the same question. So I recommend actually to learn and then look at the exams use them as a measure of how well you do. There are answers to very many questions, not all of them, very many exams, not all of them. But then, of course, you have the book also. There are answers to many of the examples. And it's really the thing to do is to work, get this in your fingers. That's the best way to prepare. The exams are fairly similar to some of the exercises in the book. And so it's really about understanding the basics and how these algorithms work. All right, so I'm going to stop recording, and then if you want to talk about projects, you can do this.